All right, let's start. So today we're going to talk about support vector machines. This is a very interesting topic because the perspective that we have on classification with support vector machines is, I would say, totally different from the perspective we had in the previous chapters. So with support vector machines, the idea is that we find a hyperplane to separate the feature space directly. So there is no probability model, there is no statistical inference, but this is more of a, I guess, computer science perspective to classification. So I'm going to start with hyperplanes, separating hyperplanes. Then we can talk about maximum modular classifier and support vector classifier. Then we can talk about maybe these two. Then kernels, and in the end, we're going to talk about performance of such a model. So let's start with hyperplanes. So let's consider that we have a hyperplane like this. So this hyperplane can be written as beta 1 x1 plus beta 2 x2 minus some intercept, or sorry, plus some intercept. So in here, let's say the intercept is minus 6 equals to 0. So in this example, so this is the x1 axis, this is the x2 axis. Beta 1 would be 2, and beta 2 is 3, right? So when x2 is 0, then we have beta 1 times x1 equal to 6. As x1 is 3 here, beta 1 has to be 2. So this is the formula for this hyperplane, and as you can see, it separates the space into two regions, the region above it and the region below it. And then the vector beta, which is beta 1 and beta 2, is actually showing the direction of the normal vector for this hyperplane. So this hyperplane is a subspace, and it has a normal vector, which is orthogonal to it. And this vector of 2 and 3, so 2 and 3, this vector in here is indeed orthogonal to the hyperplane, as you can see. So this is vector B, vector beta. Now that we have this, we can simply separate the feature space. So if x1 is a feature and x2 is a feature, then for a point like, let's say, 3 and 2, so for this point in here, this is P1. This point is above this hyperplane, and it's very easy to see that, because if we just, so let's say this is some function that defines the hyperplane. If we just evaluate this function based on this point, which is 3 and 2, we see that f of P1 would be 3 times 2 plus 2 times 3 times 2 plus 2 times 2, right? Sorry, 2 times 3, right? Minus 6. Is it clear? Yeah? So beta 1 is 2, here x1 is 3, so their product is 6, and then this one is 3, this one is 2, another 6, minus 6. And we see that this point is above the hyperplane. Then another point, if we try 1 and 1, this is P2, which is 1 and 1. We can see it, geometrically that it is below the line. And if we look at the value of the function for P2, it would be 3 plus 2 minus 6, so it's minus 1. And it's below the hyperplane. So the idea is very simple, as you can see. So now I have a question for you. What do you think the value of the function would be for a point that is on the hyperplane? It would be 0. So an example is 3 and 0. So let's just take this as P3. F of P3 would be 0 times 2 plus 0 minus 6. So it's 0, and it's on the hyperplane. So as you can see, our classification rule can be as simple as the value of the function for that instance. So if the instance, if what we're trying to classify is P1, we just check what is the value of function f. If it is positive, we classify it to, let's say, class positive or class above. That's the same thing. For another point like P2, we check the value of the function. It is negative, so we classify it to class negative or class below, right? So what do you think these values represent? 6 and -1, based on the points that we see in here.
Distance to the hyperplane.
Yeah, it's some measure of distance to the hyperplane. So as you can see, P1 is further away from the hyperplane, and P2 is quite close. And the values we got were also in absolute term. This was 6, so much larger than this one. So these are not exactly distance, but actually there's a way to make them represent some signed version of distance. So signed because we want to make a distinction between above the hyperplane and below the hyperplane. So if we just divide all the coefficients in here by the norm of this vector beta, so the norm of the vector would be 4 plus 9, so it's square root of 13. If we divide this, and this by square root of 13, we are referring to the same line, right? So the line doesn't change, but the function changes, right? And then for such a normalized function that is normalized such that the beta vector would be a unit vector, then actually these values would be exactly the distance. So that's why we can have a constraint for finding this hyperplane that would be something like sum of beta I squares over, let's say, beta j squares from 1 to p. If we have p dimensions, this should be equal to 1. So, I mean, for our example, this was not the case, but this is okay because we're not talking about support vector classifiers yet. But for support vector classifier, we want to have these values representing the distance. That's why we would include such a constraint. Any questions? All right, so the hyperplane that we had is actually a separating hyperplane. So in the feature space with two features, x1 and x2, it can separate P1 from P2, which were on different sides of that. So if our data is separable, we can just find that hyperplane and then classify according to the value of the function for each of the points. So when we have the function, then essentially that's our model, that's our classification rule. So hyperplanes in general, have this form. We have some vector x as the input, and let's say we have some beta 0 plus beta 1 x1, beta 2 x2, all the way to some beta p xp if we have p features in total. So this is a hyperplane, and this is equal to 0, of course, similar to here. So f of x is not 0. This is like the formula for the hyperplane, right? And then our classification rule would be taking the left hand side of this. The left hand side for an instance of the problem is not necessarily 0. It would be actually the representation of distance from the hyperplane. So then for some instance, like let's say x star, we're going to take so star in here is just to refer to one instance. Any questions? So this was about hyperplanes in general. So this is the representation of a hyperplane, and from that we can get this function that directly allows us to separate points in the feature space. Yeah?
Sorry, what's the purpose to make the beta sum of the beta square to 0?
So at this point, for this example, we don't have to have it, but the thing is we ideally want these measurements to exactly represent the distance, because in here this value is not 1. This distance is not 1, but here we got 1. And this distance is not exactly 6, but we got 6. So I would say the distance would be 1 divided by this. So if we just divide all of these coefficients by square root of 13, then the function that we get from that would exactly give us the signed distance of the points from the hyperplane. Yeah, so if we have 4 features, then we have beta 1 squared plus beta 2 squared plus beta 3 squared plus beta 4 squared. No, very important, this starts from 1. Because beta 0 is just an intercept and has nothing to do with this vector. So this vector in here is showing the direction of the normal vector of this hyperplane. If the vector is exactly the normal vector, which would be a unit vector, then the function would also, have that desirable property that the value would be exactly the distance. All right. So now I have a question for you. So let's say that we are doing binary classification, and there are these points. So you can see that the data is indeed separable. Yeah.
We want to make the beta equal to 1. Should we normalize the data set?
Sorry?
Should we normalize the data set?
Yeah. As all of these topics, as they are based on distance, initially we must normalize the data set. So all the features must be normalized. Yeah. So that they have a mean of 0 and standard deviation of 1, and therefore, a feature that has, let's say, 3-digit values would not impact the distances more than a feature that has, let's say, single-digit values. Yeah. So for support vector machine, as well as any other distance-based method, we want to make sure that we start with a standardized data set. All right. So let's say in here, X is tuna and O is salmon. So we want to separate these, right? So based on what we learned, the only thing we need would be just the hyperplane that separates them. But the thing is, we can have, I guess, there are many different hyperplanes. So which one should we pick? All of them, if this is training data, all of them would classify the training data set perfectly. Anyone? Sorry? This one? This one? How come? I guess it makes some intuitive sense. It is actually the correct answer, but why? Yeah, something like that. We want a maximal margin classifier. So this just makes intuitive sense that we would go with this hyperplane because it just creates essentially a margin of this much to X and a margin of, let's say, equal size to observations for class salmon. So this would be the maximal margin classifier. Of course, this is just about training data. So there is no guarantee that for the test data, this would be better than this. But just intuitively, training data is what we have access to for building the model. So it just makes intuitive sense to go with this. And how it actually performs on the test data set depends on the complexity of our model and how we have tuned its hyperparameters. So far, we don't even have a hyperparameter. So this maximal margin classifier is a good idea, but only works where if the data is separable. So sometimes we have data that is not separable. Just in that feature space, there's such overlap that you cannot just draw a line and separate the two regions. So this idea works when the data is separable, and interestingly, when P is larger than N, data is separable. So for Y data set, something that we didn't like previously, actually, so this is P being larger than N because number of columns is P and number of rows in a data set is N. So actually a Y data set is separable because we have so many features that in that high dimensional feature space, there is indeed a hyperplane that goes through, that kind of cuts that high dimensional subspace into two and classifies the training data perfectly. So I think this is one reason why, the topic of today's lecture is, I think, so exciting, because something that was like pretty much a plague for machine learning, for any other method in machine learning, now we're actually using it to our advantage. So if you have wide data set, let's say, genomic data, or let's say digital trace data, or data from some, from a situation where measuring things is easy, then support vector machines would be perhaps a natural choice for a classifier. So, but how can we find this maximal margin classifier? So let's say that we have data that is separable. Now we want to find the maximal margin classifier. So for finding it, essentially we want to maximize this. This distance is what we represent by capital M, and we want to maximize capital M over all possible values that we can have for these weights. Because these lines are defined by these betas. So we can form this as a mathematical optimization problem where the objective function is margin. We want to maximize the margin, and the hyperplane that maximizes the margin would be maximal margin classifier. So we maximize M subject to Well, we have this. This is one constraint. So sum of beta j, j from 1 to p, beta j squared should be equal to 1. And then the margin, well, essentially the classification rule is value of the function, right? So it's either negative or positive. So if we also code the classes as -1 and +1, so let's say yi is -1 or +1 to define the classes. So this is the classes for binary classification. Instead of 0 and 1, we represent them by -1 and +1. Then we're going to have yi times f of xi should be larger than m for all data points, so for all I. So when data is separable, for example, when we have more features than samples, when we solve this optimization problem, it gives us some weights, and when we use those weights in some hyperplane, that would be the maximal margin classifier. So the classification would be very simple. When we have these weights, we actually can, throw away the training data. So this is essentially a model-based learning. So we have the function, and whatever point we want to classify, we check the value of the function, and depending on whether it's positive or negative, we make a decision on the classification. Any questions? Yeah? Sorry? Yeah. So margin is our objective function. We have to connect it to the constraint of the model. So this is what we call an objective function in optimization, and this part is what we call constraints. There must be some connection between them. If we don't have this, of course, this would go to infinity, right? So the connection between m and beta is as in here, because betas are used in function f, right? So here with this classifier, so let's just go back to this. If we have classes represented as +1 and -1, then the classification rule is f of xi times yi has to be always positive. So let me give you the example. So for P1 in here, y1 is indeed +1. This is the class above. And for P2, y2 is negative because this is class below. So let's say P1 and P2 are from different classes. And as you can see, the classification rule is simply this. If the class is, if the function value is positive, predicted class has to be also positive. And if the function value is negative, which is here, the predicted class should also be negative. So this is just the rule. But so this rule only cares about points being on the correct side. So it has nothing to do with that margin, right? It's only checking whether this is below and this is above, right? But when we want the margin, instead of 0, we put the margin on the right-hand side of the equation. So when it is larger than margin, we also want to have this thing, which is m. So this difference, and let's say this distance in here, these are both m. So this idea is, let's say, is having a hard margin. So either the data is separable and there's a solution to this, or this problem is infeasible, which means that the data was not separable. This is because we were considering hard margin. We were considering that every single data point must be on the correct side of the hyperplane, which is a bit similar to fitting hard to the data, right? That's why it makes sense to also consider the soft margin. So that would be the next topic. Yeah?
So what will be the function of yi? You don't specify yi.
So let's say tuna equals -1. We just code them like this. Salmon is +1. That's it. So this is binary classification. Pretty much everything we talk about is binary classification. So we just code the classes as +1 and -1 so that we can make use of the sign of function, so that minus times minus would be plus, and that would be our decision rule.
So if that's the case, so add will be.
So this is supervised learning, right? So y values are accessible to us for training. So y values are known in here. So one constraint is based on this point. Another constraint is based on this point.
So this is y multiplied by fx is not y as a function taking fx.
Oh yeah, you're right. Yeah, actually this parenthesis was not really helpful. Yeah, it's the product. Yeah. Yeah. Is it clear now? Yeah. All right, let me just make sure I covered everything. Yeah. So there are two issues, of course, about this. Well, one issue is right here. This only works if the data is separable. That's the first issue. Sometimes the data is not separable for different reasons. One situation is when we have tall, skinny data where n is larger than p, and this wouldn't work. That's the first problem. The second issue is that here we're fitting hard to the training data, and you know that when the data is noisy, fitting hard to the data is problematic because then we're overfitting. We're also capturing noise in our model. So to give you an example, let's say if we have one additional training point. Let's say we add this training point here. This one training point is going to dramatically change the orientation of the hyperplane, because here we're using a hard margin, so our model also takes this into account and changes the orientation of this. Maybe it will be tilted like this, which is very unusual, for a model to have such a non-robust behavior. We want the model to be, essentially get some impact from the general, patterns in the data, not be affected by one data point. So that's the second reason. So if we have noisy data, or if we simulate this situation by adding one training data point to the training data set, we're going to have some non-robust behavior. So because of this issue and this issue, we would consider a soft margin, which is the next topic. Any questions?
So we say the model vector machine can solve the problem of classification.
It uses a trick. It uses a kernel trick, which manages to find the separating hyperplane in infinitely dimensional sub-infinitely dimensional space, and then projecting it back to the feature space. So if that is what you call resolving the curse of dimensionality, then yes, I would say it handles the curse of dimensionality in a very direct way. Yeah. And we are not talking about support vector machines yet. We're just building up to the idea of support vector machine. You had a question. Yes, exactly. A hyperplane always separates the space, regardless of whatever dimensions there are, into two regions. Yeah, because if we are in 3D, a hyperplane could be some 3D sort of surface, and again, there's above that surface and below that surface. That's why we're talking about the case of binary classification here. In the end, we're going to somehow find a way of generalizing this to multi-class classification. All right, let's take a quick break, and then we discuss support vector classifier.